Okay, take a look at these. I mean, they are some of the most legendary photos ever taken. Right here, we have Pluto in absolutely stunning detail, sent all the way back from the New Horizons probe, 5 billion kilometers away. And then there's this one, the famous pale blue dot, which Voyager 1 sent us from an almost unbelievable 6 billion kilometers. We've all seen the pictures, right? But the story of how they even got here, well, that's a whole other masterpiece of science. So let's get into it.
Seriously, how is that even possible? How can a tiny spacecraft send a picture across billions of kilometers of just nothing when I can barely get a good signal in my own basement? You know, forget 4G or 5G, we are talking about communication on a scale that is it's almost impossible to wrap your head around.
To give you an idea of what we're up against, the signal that carried these images is so unbelievably faint. I mean, we are talking about a whisper that is weaker than the blink of a firefly. It's even weaker than the tiny bit of energy that's released when a single snowflake lands on the ground. So how on earth do you even begin to listen for something that quiet?
Yeah, getting this data from the absolute edge of our solar system is a truly epic challenge. Think of it like this. Imagine trying to shout a secret to your friend who's in the next town over, but you're standing in the middle of a raging thunderstorm. Sounds completely impossible, doesn't it? Well, through some incredible ingenuity, we figured out a way.
Okay, so before we can send anything across space, we have to translate it. It doesn't matter if it's a super high-res photo or just some scientific readings. All that complicated information has to be converted into a language that both the spacecraft and our computers back on Earth can understand. We need a universal language for the cosmos.
And that language, it's binary code. Every single piece of information, whether it's a picture, a sound, a bit of text, it all gets broken down into a long string of just two little numbers, zeros and ones. It's the exact same principle that runs your smartphone. You know that song you're streaming? It's really just a stream of zeros and ones. Well, a picture from Pluto, it's exactly the same thing.
So how does this binary message actually travel through space?
Well, you could say it travels on a beam of light, just not the kind of light our eyes can see. It's sent using radio waves. And just like the Wi-Fi in your house or TV signals, radio waves are all part of the electromagnetic spectrum. They're a form of light, just at a frequency our eyes are built to pick up. So the spacecraft basically just beams these zeros and ones back to us on a radio wave, aimed with incredible precision right at our tiny little planet.
Now, for a spacecraft to do, well, anything, it needs power. But here's the problem. When you're billions of kilometers away from the sun, solar panels are completely and utterly useless. So where do probes like Voyager and New Horizons get their energy? The answer is pretty darn cool.
They actually run on nuclear power using something called a radioisotope thermoelectric generator, or RTG for short. So inside, there's a chunk of plutonium-238. This stuff is so radioactive that it gets incredibly hot all by itself just from decaying. Then, using a clever bit of physics called the Seebeck effect, the huge temperature difference between that hot plutonium and the freezing cold of deep space creates an electric current. There are no moving parts, nothing to break down, just pure physics at work. It's absolutely brilliant, right?
But you know, this nuclear heartbeat isn't forever. Take a look at this chart. When Voyager 1 launched way back in 1977, its RTG was producing about 470 watts of power. But as you can see, that power has been steadily decreasing. That's because of radioactive decay. It loses about 4 watts of power every single year. Today, its power budget is so low that NASA has had to make some really tough calls, shutting down instruments one by one just to keep its heartbeat. So, power is one massive problem. But the main villain of our story, the thing that makes this all so difficult, is the sheer mind-boggling distance that signal has to cross. The vastness of space isn't just empty, it feels like it's actively working against us. I mean, light is fast, right? It's the fastest thing in the entire universe. But space is just so vast that even light needs a long time to get anywhere. If we send a command to Voyager 1 right this second, it will take 23 hours for that message to even get there. Then we have to wait another 23 hours for Voyager's reply to travel all the way back. That's a 46-hour round trip, a 2-day delay for a single text message, basically. And that's not a bad connection. That's just the laws of physics.
But the real killer, the thing that makes this whole thing seem impossible, is a fundamental rule of physics called the inverse square law. It's the reason this is so hard, and it's almost beautifully cruel in its simplicity.
Here's how it works. Pretty simple, really. If you double your distance from a signal source, the signal doesn't just get half as strong. Nope, it gets 4 times weaker. That's 2 squared. And this effect just gets worse and worse, really fast. Check this out. Move 10 times farther away, and now the signal is 100 times weaker. Now just try to imagine that effect stretched out over 6 billion kilometers. The numbers get crazy.
So here's the bottom line. Voyager's transmitter sends out its signal with about 23 watts of power. That's less than your refrigerator light bulb. By the time that signal finally gets to Earth, it has a power of less than 1 attowatt. An attowatt, that's a billionth of a watt. The signal is almost completely gone. So how in the world do we hear it?
This is where the human ingenuity really kicks into high gear. If you can't make the shout any louder, well, you only have one other option. You've got to build much, much bigger ears. And that is exactly what we did.
Let me introduce you to the Deep Space Network, or DSN. It's a global network of the biggest and most sensitive radio antennas on the entire planet. They are strategically placed in California, Madrid, and Canberra, Australia. And there's a very clever reason for that. Those 3 spots are separated by about 120 degrees of longitude. What that means is, as the Earth rotates, we always have a complete 360-degree view of the sky. There are no blind spots. We're always listening.
And when I say these antennas are big, I really, really mean it. The main dishes of the DSN are a massive 70 meters across. To put that into perspective for you, that is roughly the width of a professional soccer field. You need an antenna of that colossal scale just to scoop up enough of that incredibly faint signal from space to even have a chance of detecting it. But believe it or not, even a giant dish isn't enough. The signal is so unbelievably weak that it can get totally drowned out by the electronic noise from the antenna's own equipment. So what do? They cryogenically cool the receivers with liquid helium down to nearly absolute zero. We're talking minus 273 degrees Celsius. This basically makes the electronics go silent, quieting the noise to almost nothing and allowing the antenna to finally hear that tiny, tiny whisper from the very edge of our solar system.
So you take all this incredible technology, the nuclear power, the giant antennas, the cryo cooling, and it all comes together to let us receive not just data, but these moments of just profound perspective. And that brings us to one of the most famous photos of all time.
So, on February 14th, 1990, a full 13 years after it launched, Voyager 1 was given one last command from home. It was about to leave the solar system forever, but before it did, the team at Mission Control asked it to turn its camera around one last time and take a picture of home.
And this is what it sent back. A single pale blue dot just hanging in a sunbeam from 6 billion kilometers away. That's us. All of our history, all our triumphs and tragedies, every single person we have ever known and loved exists right there on that tiny little mote of dust. It's just incredible. And after taking this photo, Voyager's cameras were shut down forever, just to save power for its long, lonely journey into interstellar space.
Voyager 1 is now the farthest human-made object from Earth, and it's still going. It carries with it a golden record, kind of like a message in a bottle, with sounds and images from our world. It's a greeting card for any civilization that might find it, maybe thousands of years after we're gone. And that kind of leaves us with a final thought, doesn't it? If we had the chance to create that message today, right now, what would we want it to say about us?